Hello everyone, my name is Levi McKinney. I'm a first year grad student at Georgia Southern University. My co-author is Amanda Weaver. She is a senior undergrad, also attending Georgia Southern University. The both of us work in the automotive and aerospace combustion labs under Dr. Valentin Soloiu. A little bit of background and motivation for this project. There are a lot of systems in the aerospace application or field that create an excess amount of heat, which could potentially be transported away from vital components and therefore be transferred into something usable, say electricity. My overall focus is to take the fluids that are cooling these different parts of aerospace application, i.e. the engines or turbines, and increase the thermal conductivity of the fluids that can therefore remove the excess heat at a much faster rate. And the way that I want to experimentally determine this is by adding different types of nanoparticles to the fluids in order to increase the overall thermal conductivity of that fluid in order to therefore increase the efficiency of the system. The reason I chose nanoparticles is because of their size. Being as small as they are, they're less apt to clog up different types of filters that could be in the system. And also determined I wanted to use a plate style nanoparticle as well, because these atoms, they carry 20% of their surface area or their overall area on the surface of the plates themselves. Therefore, they're able to conduct heat very well. And whenever you add these nanoparticles to the fluid, it decreases the specific heat of that fluid, that therefore it requires less energy to raise the overall temperature of the fluid and also to cool it as well. The way that I plan to test this first is to consider the fluidic properties of the nanofluids. So we'll take and measure the viscosity of the fluid that we're going to use first, and then add the nanoparticles to determine the viscosity of the nanofluids after they've been added. And the way that we plan to turn this excess heat that's coming off of these systems is by using a Seebeck apparatus that will utilize the wasted thermal energy and utilize it to transform it into electricity. So far, we do have a test bed that has been designed, and it contains components such as the thermoelectric generators, a Grundfos pump, type K thermocouples, pressure transducers, laminar flow meters, and the pressure transducers and thermocouples, they're going to be used in order to measure the pressure that is occurring inside the system, and the thermocouples will be used to determine the rate of heat transfer as it's moving through the thermoelectric generator, as well as there in number 5 on the picture there, figure 2, the number 5 block, that represents a radiator that is going to be in the system, and the thermocouples will be measuring the inlet and outlet temperatures of that to be able to determine how much heat is being lost or transferred through that radiator. My current research, it suggests that whenever we're running tests on the copper oxide concentrations of 0.5, 1, 3, and 5%, that the viscosity as the temperature increases is going to decrease along with that increase in temperature. Also, if you look at the graph for the Nusselt number versus Reynolds number, my research suggests that as copper or aluminum is added into the water, we're going to see an increase in our Nusselt number as compared to the Reynolds number. So the thermal properties of the nanofluid, there are several things that affect it. The viscosity obviously is going to increase whenever we add nanoparticles into the fluid, which is why that part is so important. And our thermal properties, they're determined using specific heat, thermal diffusivity, the density of the fluid, Nusselt number, and heat flux. All these are very important things in order to determine the thermal properties. But the addition of the nanoparticles will increase the thermal conductivity of the system, even though that, with a rise in viscosity, it's going to increase pumping power a little bit. I believe that the increase in thermal conductivity will be worth that increase of pumping power. So the main three things coming out of this research thus far is that the addition of the nanoparticles, they increase the heat transfer of a fluid exponentially whenever they're added in, and that transferred heat can be used to create small amounts of power through the thermoelectric generators, utilizing that wasted thermal energy, and increasing the heat transfer of the fluidic cooling systems can increase the overall efficacy of the thermal systems by removing that excess heat on a much faster rate than it was occurring before. So this is where we're at with this research thus far. Our next steps is actually to build this system and get it up and running to physically do these experiments and determine what we're going to see happen more or less in the real world applications of this. As I said before, this is a design, this is a plan, and we plan to execute this, and it should be up and running hopefully by the end of next semester, to where we're doing full experiments, adding our nanoparticles, doing our viscosity test, and determining how much the thermal properties are being affected by the addition of the nanoparticles.